Hello everyone, I am Miguel Alfonso Mendez from the Karman Institute for Fluid Dynamics, and with this video I'm happy to start a series of tutorials dedicated to data-driven modal decomposition. These tutorials are focused on the use of MODULO, which is a software package developed at the Karman Institute together with my former master's student Davide Ninni. Davide is currently carrying out his PhD at the University of Bari, but he is still actively working on MODULO, and you can contact both of us for questions, suggestions for future development, or simply for some feedbacks. Davide was the main developer of the Graphical User Interface, and he will guide you through the installation and the use of the software through several exercises. In this and in the next two videos, I will focus on the mathematical framework of the decomposition available in the modulo, the main one of which is the multiscale proper orthogonal decomposition. In this first video, I will give you a general introduction on data-driven model analysis, and it is divided in two parts. In the first part, I will recall what is data-driven model analysis, and in the second one, we will review the fundamental of orthogonal projections and reduced models. So, what is data-driven model analysis? In this work, we refer to a branch of data processing that takes a set of data and breaks it into a linear combination of elementary or rank 1 portions that we call modes. We will usually assume that the data has been sampled over space and time, but of course you can think of different independent variables. In our setting, each of these modes has its own spatial structure and temporal evolution. There are mainly three reasons why you might be interested in doing this, and depending on how you use these modes, you enter in different areas of applied mathematics. For example, you might wonder if any of these modes describes a coherent pattern or feature in the data. In this case, you would be doing pattern recognition and or classification. The quest for identifying coherent structures in turbulent flows was historically one of the main drivers of this field in fluid mechanics. Here I show you an example of time-resolved particle image velocimetry measurement of an impinging gas jet, together with the dominant coherent structures describing the roll-like vortices produced by the Kelvin-Helmholtz instability in the jet. This turned out to be well described by a single mode. Or you might wonder if some of the modes are irrelevant or maybe even associated to undesired features that you want to remove. Removing modes, you're doing data compression or filtering. Here I show you an example of such an application for video processing. In this work we have developed an algorithm for particle image velocimetry, which can do a great job in removing background noise such as reflection. This algorithm is based on modal analysis of the grayscale videos. We can show in fact that there will usually be some modes linked to background reflections and noise, and other modes linked to PIV particles. So by projecting the first and giving the second, you can obtain beautiful and noise-free PIV images. Or you might wonder if some of the important modes can be used as a basis for reducing the complexity of a problem. In this case, you enter in the realm of reduced order modeling. Here the goal is to combine data-driven model analysis with numerical schemes. By projecting a problem onto the basis spanned by few of the leading modes, we can convert partial differential equation into a very reduced set of ordinary differential equation and then significantly reduce the computational cost. Here's an example from an exercise I usually give in our data processing course. The exercise consists in solving a problem using finite difference methods and reduced order modeling. This is the velocity profile of a Poiseuille flow subject to pulsation on the pressure gradient. You have a comparison between an analytical solution using 15 eigenfunctions of the problem, in this case of the Laplacian operator, a numerical solution using 1024 mesh points, and a numerical solution using a reduced order model that combines only the first three POD modes. You can see that despite the enormous difference in the number of degrees of freedom and hence in the cost of the simulations, the resulting velocity profiles are in good agreement. Now, although this seems very different application of a great interest to any area of applied science, it is very interesting to note that they are all based on a very simple fundamental framework, and this is what I want to review here. So, every dataset is a collection of points that arise from some sort of sampling or discretization process. Consider for the moment a 1D signal, which is a function of time. Although not every decomposition requires this, we will assume here that the signal is uniformly sampled, and k is the index that starts from 1, in which case we have the time 0, and continues up to nd. That is the number of points that we have collected and stored. After discretization, our signal becomes an array of values, and we will here use interchangeably two notations. If d of t is the notation for a continuous signal, d of tk refers to a discrete signal sampled along the discretization tk, while dk with square brackets refers to an index notation that ignores the link with the original domain. So in this case, our signal is a column vector. The very notion of vector implies the notion of a basis. By default, we consider our vector to be in the Cartesian basis, which in signal processing is seen as a set of shift impulses. So this vector here is a combination having d1 times the first impulse, d2 times the second impulse, d3 for the third, and so on. The notion of discrete transform and modal analysis arise when we decide to use another basis to represent such a vector. In general, our vector would be a linear combination of some basis vector with a set of coefficients that I usually indicate with C's. The operation of moving from the impulse basis to the new one can be easily seen in terms of matrix multiplication. In particular, we construct the matrix basis B by collecting all the elements of the basis along the column of this matrix. Then we can collect our set of coefficients as a column vector dp, which represent our transformed signal. It's the representation of our vector in the new basis. Now, this multiplication gives us the original signal and is therefore an inverse transform. Given the set of coefficients and the basis, we can represent our signal d. To compute a transform, we need to compute these coefficients, so we need to invert b. So you understand that in order to move back and forth from one representation to the other, we need b to be invertible. So we need to have at least linearly independent basis elements, and this is what happens with all the decompositions that we will consider. Now, if we get used to see signals as vector, it is interesting to see what are the operations that we usually do with vectors and what is their link to signal processing concepts. The fundamental operation in any vector space is the inner product. The inner product between two vectors of equal length is a scalar constructed by summing the element by element product, taking the conjugation of one of the two vectors. This is something you need to make sure that the product of a vector with itself is never a negative quantity. In vector notation, we will replace this summation by a vector product of b dagged times a. Here, the dag denotes the Hermitian transpose, that is the transpose and the conjugation. What are the key operations using this inner product? The first is to compute the length of a vector. That is the inner product of a vector with itself, and you understand why this can never be negative. In signal processing, we call this energy. The second is linked to projections or degrees of similarity. We can use the inner product to compute the angle between two vectors or two signals here. You might remember from high school that the cosine of the angle between two vectors is the real part of the inner product over the product of the lengths of the two vectors. This is a quantity that can go from -1 to 1. In signal processing, we call this correlation. So if we have 0-degree angle, that is, the vectors are aligned, we will say that we are dealing with correlated signals. If the angles between these is 90, so the cosine is 0, then we talk about uncorrelated or orthogonal signals. Orthogonality or non-correlation, and more specifically orthonormality, is a beautiful property to ask for the basis vector of any decomposition. Why? Because in this case you can easily see that the set of inner products between different elements of the basis gives either 1 if you're considering the same basis element, or 0. In other words, if we do big dog times b, we get the identity, and that is equivalent to say that the inverse of the matrix B is simply the Hermitian transpose. So in this particular case, we can move back and forth from the Cartesian to the transformed domain by using simple transposition, which is computationally much easier to handle. Moreover, all orthogonal bases can be seen as rotation, so they preserve the length of the vector from one basis to the other. That is to say, we preserve the energy of the signal as we change the basis. So here are some suggested readings, at least my favorite books on orthogonal transforms and signal processing. The first is from Professor Wang and is a very complete review of orthogonal transforms in general, both in continuous and in discrete domain. The second one is the book from Professor Alan Broughton and Professor Carl Bryan, and it's focused on the two most popular transforms in signal processing. These are the Fourier transform and the wavelet decomposition. And the third one is from Professor Julius Smith and is a very accessible and complete review of the discrete Fourier transform. In these books you will see how the very simple concept from linear algebra that I have introduced applies to a huge variety of signal processing operations. For the purposes of this work, it is important to understand that in classical linear modal analysis, every mode is composed of three parts. We have an amplitude that tells how important every mode is, a spatial structure that represents a basis for the space domain, and a temporal structure that represents a basis for the time domain. To see how the concepts I have previously introduced apply to the modal analysis, you first need to get used to see datasets as matrices. So consider, for instance, a 2D velocity field produced by particle image velocimetry. This is the flow of a 2D impinging jet on an horizontal wall. And let's say that we have nx points along the horizontal axis and ny points along the vertical one. If you look at one specific time step, how many degrees of freedom do you need to univocally define the step? Well, you need 2 times nx and y because you have two components. So in this, if this was a scalar field, you will have nx times ny, and if this was a 3D volumetric PIV, then you will need 3 times nx and y. It is convenient to reshape the information contained in every snapshot in every single time step as a column vector. Here we will take all the u components column-wise and stack them one below the others, and then below this we will do the same with the v component, the vertical component. The criteria you use to reshape the snapshot is irrelevant as long as you use the same when you want to get back into the space domain. Now, if we put every snapshot as a column of a single matrix, you build your data matrix. And here we have as the time evolution along the rows and the space distributions, let's say, along the columns. So the first row, for instance, tells how the data evolves in time in specific degrees of freedom. In this example, is going to be the u component in the bottom left corner. We can now look at this matrix from two different perspectives. On one hand, we have the space view or row dynamics. Every column or every snapshot is a linear combination of spatial bases represented by the phi's, and the coefficients of this linear combination change in time. What controls the temporal evolution of this coefficient is the set of basis element in the time domain, that is the psi's. So here we are following the dynamics of the data from the spatial basis. On the other hand, we might have a time view or column variation. Here we see every row, every time evolution as a combination of a temporal basis, that is the size, and the coefficients of this linear combination change as we consider different spatial locations. What controls the spatial dependency of these coefficients is of course the set of phi's that is the basis for the space domain. However, regardless of your choice, you're looking at the same data from two different perspectives, and this should tell you that you do not have the freedom to choose these bases independently. Temporal and spatial bases are linked. In general, it is a good idea to impose that both the bases have unitary length, so that the sigmas are the only representative of the contribution of each mode. Moreover, it is convenient to write this linear combination as the sum of outer products. Each of these outer products produces a matrix of the same size as D, and together with its amplitude represents a rank 1 approximation of the data. If we sum all the possible rank 1 contribution, then we can reconstruct the original data. In particular, you should observe from this equation that the number of non-zero sigmas that you have, regardless of the basis that you choose, is equal to the rank of the original matrix. So if we include a number of modes equal to the rank of the matrix, we are not doing any approximation, but we are representing the complete data. Now, this set of outer products can be written as a matrix factorization, which in this work we indicate as follows with a phi sigma psi transpose. Here the phi matrix contains along each column all the elements of the spatial basis, while the psi contains in each column all the elements of the temporal basis. In the middle we have a diagonal matrix sigma that collects the amplitude of each mode. Observe that here I put the transpose simply because I want to keep the column nature of every basis vector. If we were in class now, some of you will comment that this factorization looks a lot like singular value decomposition, and that would be an excellent observation. Yes, this looks like a singular value decomposition, but I want you to keep in mind that the SVD is only one of the infinite factorization of this form that you can create. In particular, there are two key observations here. First, since sigma is diagonal, you are not free to choose phi and psi independently. As we said before, you can only fix one of the two, and you can complete the factorization accordingly. In this work, we will be generally more interested in the temporal evolution, so we will fix the psi's and then compute the decomposition accordingly. The second observation is that if we decide to include only some of the available modes, say R smaller than the rank of D, then we have a filtered version of the data, which I will denote with tildes in the following videos. And the result is a reduced order model or reduced rank model of the original data. So I will conclude this video by recalling that how all the decompositions in Modulo work. They all start from the definition of the temporal basis, the psi's, and every decomposition, as we will see in the next video, has its own way of computing the psi's. Generally, psi would be invertible. In fact, it will even be orthogonal. So, in general, you can multiply this expression by the inverse of psi transpose, and you obtain phi sigmas. And you should recall that we asked that each of the spatial basis element have unitary length. So by normalizing each of the columns of this product, we can directly obtain the sigmas, so we can assemble easily our inverse sigmas, and compute the spatial structures. So these are the key steps for every decomposition. You get your data matrix, and by reshaping every snapshot as a column vector, then you compute your size, and this is the only step that depends on the decomposition. We will talk about data-driven decomposition when we calculate this psi depending on the data that we have, when we tailor our bases to the data that we have, and we don't pre-compute it a priori. The third step is then the projection to compute the spatial basis from the data matrix and the temporal matrix. With this, I think that I gave you enough background to understand the following videos, and in the next one we will see how this concept applies for the discrete Fourier transform and the proper orthogonal decomposition. So see you in the next video.